Yeah, please.
So this project is based on the project from Randall's Center for Maternal Health, Infant Health. It's about to predict the postpartum hemorrhage using machine learning algorithms. And it's also part of my submission for the chip certificate as a NLS 793, the practicum. Okay, so let's begin. By the way, this is my birthday.
Oh, well, hey, that's all right.
And my mother was nearly killed. Yeah, my mother was nearly killed, giving birth to me by PPH. So I think it's very, significant that God's arrangement for me to get engaged into this project. Okay. So the background, PPH is defined by ACOG as a blood loss greater than or equal to 1,000 ml. So I use this 1,000 ml as threshold to classify the blood loss after delivery as non-PPH or PPH. So it's basically a classification problem. And PPH is one of the leading causes of death related to maternity. So, and there are panels and experts, they have done some research saying that PPH can be prevented. And if we anticipate the occurrence of it before the delivery, so it is significant to do PPH prediction to save lives, okay? And USA Today has published articles and highlighting that NC hospitals, they are singled out as has done a bad job, preventing PPH. So that's motivation, the motivation of our project. So the motivation also includes the following statements. First of all, the current mechanism used by UNC Medical Center is based on EPIC. It's based on the AWHONN. I don't know how to pronounce the acronym. The Association of Women's Health, Obstetric, and Neonatal Nurses. But this project, PPH project, this project has fatal flaws. First of all, it is oversensitive. It is flagging so many patients as high risk. This can lead to two problems. First of all, this anticipatory interventions for patients who are considered high risk will lead to enormous waste of time of this blood bank and of this nursing time. And because this oversensitive mechanism, many doctors nearly abandon these warnings. They don't heed the warnings because this alarm fatigue. Okay, so that's why we want a new mechanism, new system to better predict, of this PPH based on machine learning. The machine learning is a trending way of including deep learning to solve, prediction problems. The data collection is owed to Randall. Randall delivered the data from, he collect data from Epic Clarity. It's a relational database. And Randall did a good job extracting, transforming, loading, integrating. So the data is from the actual records from the patients from UNC Women's Hospital. It's very significant to our study because we are doing our prediction based on the actual data, patient data. So it has because the demographic has differences over states and over countries. So we cannot use, for example, the data from Japan or data from some South Africa hospitals. So we use the data from UNC Women's Hospital. So it's more pertinent to our practice in the hospital. Okay. So we have 12 variables to predict. The last variable is our target variable. The blood loss total is a ppH. Among these 12 variables, we have the race, the age, the gravida. Gravida is the number of confirmed pregnancies. Para, the number of births that a woman has had after 20 weeks gestation. So these two variables, gravida and para, they are closely related, but they're not same. PUS is the prior uterine surgery. It's a binary one, multiple is a binary one. MBP is very important. It's kind of BMI of the patient. And the pre-VUCS, whether it's binary value, whether the woman, the patient has previous C-section or not. DSLC is the days since last C-section. And the GA, the gestational age, the age of the woman when he was pregnant. Okay? And the DEL type, delivery type, including the multiple C-section, is the multiple value, including C-section, and vaginal, okay, and otherwise not known. Others, induction, one is a binary, whether induction was performed. And the target value are blood loss total. It is based on two other variables. It is sum of blood surgery and the blood loss during the surgery and the blood loss on the flow sheet. Okay. So we are using these 12 variables. The 12 variables are not arbitrary. We are using them based on some literature review and our discussion with the medical providers, nurses, doctors from Women's Hospital. So we'll see whether the 12 articles are pertinent to our target in the later slides. So the first thing we got data is to do some EAD, like exploratory data analysis. So this graph shows that the attributes, the features are of great scales. They have very different scales. For example, we have 8,000 here, but we only have 8 here. So the difference of scales will lead to errors in our machine learning algorithms. Machine learning does like its variables to be of very different scales. So we have to normalize these variables using standardization. It's kind of I use Python. There is a Python library standard scaler to scale, to normalize all these variables. We have other options like min-max. Min-max is a very popular way to normalize variables, but it does apply to our case because min-max assumes the values of these features are not dispersed. But we have very dispersed values like this one, like this one. So if we use min-max, it will lead to errors. So we use another way, standardization. This way is not does not assume that these values are concentrating. Okay, so it's another way to explore data to see the linear correlations between the variable. The less dispersed, for this one, the less dispersed the points are, the more correlated the two variables are. For example, this line and this column, they are same. It's a mirror. It's mirror. The diagonal is kind of against itself. It doesn't make sense. So from this graph, we can see that age and MBP are closely related to our target value, is a ppH. And we can also see that, for example, gravida gravida and the para, they are of less correlation because you can see the points are very dispersed. So it means that MBP and age, they are linearly greatly correlated with our target value. But for these values, for example, gravida, para, and multiple, when the points are dispersed, we can also assume that these variables, they carry information that are not captured by other variables. So this is a way to interpret this graph. The dispersed points means this variable can carry new information that not captured by other variables. And the concentrated points means this variable and this variable are closely related. But like this heat map, this heat map, but they only explore the linear relationship between the features. I can notice that we have dummified the race feature and the delta feature because they are categorical, they're not numeric values. So I dummify them into binary features. For example, race including Latino, Asia, Black, other, and white. So I expanded this one column into 5 columns, 5 features. Each feature is a binary value. For example, this feature means whether you are Asian or not. So I converted this text value into numeric value so that the machine learning can use it. It's also the case with the delta type CS of vaginal, okay? So it's a binary thing. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so 13, 14, 15, 16. We have like 17 features after the dummification. So next step is data processing to process the data for machine learning algorithms. The first one, data cleaning, to fill in the missing values. We don't have many missing values in our case, but we can use Python. There is a value like computer to fill the missing values with median or average of the whole column, or we just fill in the zeros. I use median. I use median I use median to fill in missing values because it make more sense than filling them with zeros. And as we all know, when we are dealing with medical data sets, chances are that the data set are not balanced. For example, the non-PPH and PPH are extremely unbalanced. PPH cases only account for like 11% of the whole observations. So we have to, but this unbalanced data is very bad, detrimental to our machine learning algorithms. So we have to use balancing, oversampling, use SMOT. SMOT is a kind of a method to balance the data set according to some variables. Okay? So we oversample our cases to get balanced data set of PPH and non-PPH. A recursive feature examination is RFE. And this is very important. We select features by recursively considering smaller sets of features. This mechanism to use this method, recursively considering smaller subsets of the features to see whether one feature contributes information to our prediction. Okay, so we use this RFE to measure the performance of features from the training data. to see whether one feature is of no significance or of no use to our predictive ability of the model. It turned out all the 12 features are of significance to our predictive ability, so we didn't drop any feature. And dumpification, as I mentioned, dumpification is, we dumbify, we convert those categorical like a race and the data type, delivery type into numeric using this function, getDummies function. So this like a pipeline. We can summarize this into a pipeline to pre-processing the data set. The models, so our study is to compare different models to see their ability to predict pH. So the models we selected are very popular models used for classification tasks. For example, logistic regression, decision trees, random forest. You can see from this graph that the random forest is kind of multiple decision trees, and we use the majority voting to come up of the final result. So this one, I assume this one is better than this one because it's built on this one. And KNN means K nearest neighbors, and ANN and SVM. I didn't use a SVM because the space SVM. The 6 ANN is artificial neural network. It's very popular nowadays. It's a deep learning algorithm. I use one deep learning to see whether deep learning can perform better than this machine learning. But deep learning is kind of a branch of machine learning. After some calculation, we will evaluate the models because it's the most important part of our project. Evaluate the performance of these models. Based on it, we can do comparisons. So the most important 2 metrics. The first one is cross-validation. Cross-validation is for other projects we can divide our data set into training set and the test set. But for cross-validation, we divided randomly the data set into 10 folds. And we use 9 of them as training set, 1 as a test set. Then we iterate until all the holdout fold is used as a test set. And we calculate the average accuracy of the 10-fold. This is a cross-validation. It's a way to we have this average accuracy value to evaluate the models. The other one is our CLC, like the false positive rate and the true positive rate is very significant in evaluating classification task. We have also an area under curve, AUC value associated with this graph to evaluate models. For example, we have this, figures. The more area covered under the line, the curve, the more able the model is to predict, the pH. So from this graph, we can see random forest is the best one, and SVM they are different from the ROC metric. So if we want to distinguish between our SVM and the random forest, we have to use other metrics. This is the accuracy. Accuracy is we calculate accuracy based on this formula. The true positive, true negative is a numerator, and the denominator is a true positive, false positive, true negative, false negative. I think it's very straightforward metric to evaluate the models. It turned out that against the test accuracy, this one is more significant because training accuracies, we can ignore it because it can be the result of overfitting. Random forest stands out as the best one. And then artificial neural network, ANN. Then KN, then SVM, this is actually logistic regression. So this graph told us that random forest is also the best one in its accuracy. This is the contingency, like the contingency map, except for ANN. We cannot use ANN. We don't use confusion matrix for ANN, for deep learning algorithm. So we can see the, for example, this is the cases of true positive. This confusion matrix is also a way to evaluate models of classification. This is the summary of all the metrics. We can see that the random forest is the best in terms of all the metrics, like precision, like recall. F1 score is based on precision recall and accuracy, and is CV stands for cross validation. This tenfold cross validation, accuracy, average accuracy. So random forest is the most promising one in predicting the PPH in our case. And the ANN is second best. Feature importance is also a very important metric to interpret our machine learning models. So based on random forest, our winner, based on this algorithm, I calculate the feature importance. It's very easy because Python has a library feature importance. I just use library to come up with this visualization. It turned out that MBP, BMI, is the most significant feature to predict, and not correlation. It's not correlation. It's not like the feature, the graph we talked before. We use random forest to calculate the feature importance. MBP, the most important one, and the GA is also age of gestation, which when the patient is pregnant. Gravida, number of children, DSLC is days since last C-section. So even POS, the least two ones, delivery type, other delivery type unknown. So these two ones are the result generated from our diamplification. It's a binary, so these two features can be safely removed from our data set. But POS, aside from these two, all the other features contribute to our predictive ability of random forest. Okay, so this is very important one to interpret our machine learning model. We can use this graph against other models, algorithms like logistic regression. But since this is the winner, so we built it on random forest. So discussion one, we should think about why random forest and ANN have the best performances among all the models. I think they have one thing in common. These two algorithms. Their images have something in common. Random forest and ANN, they both exploit interactions between features, and they don't assume the features are linearly correlated. I think that's one of the best, one of the most important reasons why these two algorithms, they stand out as the best ones. For example, random forest, they reduce the variation of the data points. So by doing so, they improved accuracy. And they use as many as decision trees and get the final result by majority voting. And ANN automatically extracting the correlations, exploiting the correlation between features, not assuming that they are linearly related. And limitations. First one, according to some literature, we know that the measurement of UNC Women's Hospital is not perfect. We use some non-calibrated collector bag, and at the end, blood loss is visually estimated by looking at the blood-soaked supplies. So the pH measurement are not quantified, perfectly. So our target feature, we have some error compared with the real blood loss. And data quality, we only have less than 2,000 data points. I think the first batch of data set Randall delivered to me, Randall will have more data coming up. So the first batch is only less than 2,000 data points. This number is far from adequate to build state-of-art model to predict pH. And ANN, deep learning models, they favor large data sets. So I assume before the study, ANN will be the winner because deep learning is more, more complicated and more able to extract the granular aspect of features. But since we have limited data points, ANN doesn't perform well. I believe in the future, if we have more data set, ANN will be the best one. Deep learning will be the best one. That's the reason for deep learning.
I have a question. I don't come from the area, but I consider it extremely interesting, your point of view, in order to get the approach of the theme. We assume the variables that you receive, no? From what happens if we reduce the quantity of variables before to run the machine learning models? It's possible to get different outcomes. For example, could be possible that random forests don't get the first position as the best predictor if we have changed the drivers, or we have eliminated some drivers before to try the machine learning models?
Okay, so you mean, for example, we remove these variables and only use these ones, for example, the first 5 best ones to run machine learning models. I think the accuracy wouldn't be very different. I tried removing POS, the last 3 ones, I removed them from our data set, and the accuracy is pretty much the same. But I don't know whether we can, for example, PS, even if it's small, this contributes some information to our predictions. So there's no reason we remove it. There's only one reason we remove the number of features, is that the number of features is less than the number, is more than the number of data points. For example, if we are dealing with the text, we have tens of thousands of words as features, but we only have like 1,000 data points. In that case, we will reduce the dimensions, that reduce the number of features dramatically. Use PCA or chi-square algorithms. But in your case, we only have like, after duplication, we only have 17 number of features, and we have thousands of data points. So it doesn't matter whether we remove the features or not, the accuracy will remain pretty much the same. Yeah. But in in other cases, if the number of features exceed the number of data points, that will be a problem. It will lead to overfitting.
So I think it may be interesting to reduce number of variables from an operational perspective, because then you don't need as much information, clinical information, to get accuracy, right? So
yeah.
that is maybe from an operational perspective at the hospital is easier. It's better, I guess, to have the minimum number of variables that stick without sacrificing accuracy at the moment.
I will try. Remember, I mentioned this recursive feature evaluation, this algorithm. This one is, answer your question. We use different subsets of our data set, different number of features to see whether a feature contributes information to our predictions. So the result is all the features are considered, useful. Useful to our predictive model. So we didn't eliminate any of the 12 features because they are. But if we, from the practical point of view, like Randall said, if we want to use as few as possible number of features to do the prediction, we can select. For example, we can have a threshold, something like that. For example, this one, because we see that the race and delta doesn't matter much. Okay, so from this one, so we use these features to run the machine learning models to see whether the accuracy or other metrics vary much. So I will try this. If I need, I will try this one. I tried this one actually. I removed the last three one, and it turned out that the accuracy is the same.
Thank you.
So, yeah, fantastic job. I love the way you conceive of the problem and how you have explored the problem. I remember you from my class. You were so quiet most of the time.
Because when I was